Okie dokie, chemists, let's get started. So we're going to jump right into chapter 6 today. To expedite things, I updated the chapter 6 lecture module page. So if you navigate there, you're actually going to see 2 additional sets of lecture slides. One's with the blank normal slides, and the other one is actually annotated already. So I already have a lot of the blanks and stuff filled in just to help expedite us through this chapter. So if you're following along on your iPad, please download those annotated slides, whether 1 per page, 2 per page, or whatever. And also, my goal is to finish this chapter before fall break. We're going to cut it close. I'm not sure if we will. But if you want to jump ahead on midterm preparations, I already have the lecture recordings from when I taught this last year. So if you want to get ahead, they're there. But I will still post, obviously, these lecture videos or lecture recordings right now on the same page, but this is if you want to get ahead. So all the information is there for you to prep for the exam. Remember, all 5 practice exams are already posted, so you have this weekend. It's going to be cold, so why even go outside? Just stay in and study chemistry. So you can have a nice fall break. Okay, so that's there. Okay, so we will jump into chapter 6. So I'll say, so in this chapter, we're going to talk about the electronic structure of the atom. So to prime ourselves, if you took chemistry in high school or whatever, if you recognize the terms like s orbital, p orbital, does that sound familiar? And if it doesn't matter, okay? It's better to learn it correctly from me the first time anyway, or like d orbital, all right? You learned what these shapes were, but I feel like in high school you don't learn why. Why does a d orbital look like a butterfly? Why does a p orbital look like a dumbbell? Why is an s orbital spherical like this? And so in college and in this chapter, we will dive deep into why these shapes are the way they are. And all these shapes are actually electron clouds. So they are, the probability of finding an electron with this energy will look something like this. And so we'll talk about the significance why electrons have these electron clouds associated with them. And the moral of the story is stuff gets real weird when it's small. All right, that's basically the whole premise of this chapter. So in chapter 6, we're talking about atoms and electrons. So that feels like a big deviation from last chapter where we talked about like calorimetry, thermodynamics. Isn't that like, it feels like they're not related. And so like the first few times I taught this class, you know, that's how I prefaced it. But I feel like now that I'm a better teacher, I actually can relate these 2 chapters rather well. So let's think about this equation. All right, what kind of equation is this? Fuel plus oxygen gives us CO2 and water? Combustion, yeah. So we can, with our chapter 5 skills, tell me the sign of delta H of a combustion reaction. Don't think about it too hard. Negative, yes, all right. So let me just draw this out. So we have fuel and oxygen. Those are my reactants. And so we can draw like an energy coordinate diagram that says, oh, we go from reactants to products. The products are more stable than the reactants. And we see an overall decrease that is related to our negative delta H. All right, so that's a combustion reaction when we burn stuff. Now let me change the language a little bit. As humans, we eat stuff in terms of fueling our bodies, right? We fuel our bodies so we can teach for 5 hours straight, like on a day like this. What else do we have to put in our bodies? What do we breathe? Oxygen, yeah, we breathe oxygen. And what do we exhale? What are our products, our excrement? CO2. And so what is it called when we work really hard and we burn fuel, when we burn our calories? When we say we blank our calories? Burn calories. Don't we burn calories, right? And so really what humans are doing, we're taking fuel, the food that we eat, we're breathing in oxygen, we're breathing out CO2, so we can harness that exothermic reaction to fuel our bodies throughout the day. And we call it burning our calories, very similar to that of a combustion reaction, because it is a combustion reaction. We're just doing it really, really slowly. all right? Okay, so that's in the forward direction. We are just little combustion engines, all right? Taking fuel, oxygen, making CO2 and water. So that's the forward reaction. Let's think about the reverse reaction. So the reverse reaction is, what sign of delta H is the reverse reaction? Positive, yeah, we go up the hill. Okay, good, good. All right, what do plants do? What do plants breathe? CO2, and what else do you have to give plants so they live? Water, cool, all right. And then what do plants exhale? Oxygen, yeah, and don't they make us our fuel? Like if we eat plants, like vegetables or whatever, all right, they're our source of fuel, right? So really, plants are just doing the exact thing we're doing, but in the opposite direction. But here's the difference, that yes, they're doing the reverse reaction, but delta H is a positive number. So plants actually require energy to do the thing plants do, right? They need to get energy from something else because that is an endothermic process. What else do plants need to live? Sunlight, yeah, so sunlight can come in. Sunlight is the form of energy that plants use to go up this thermodynamic hill that we need to go up. Sunlight is the reason plants can take CO2 and water, go up the hill, and do this reaction in reverse. And so in this chapter, we're going to talk about light a lot and how light has to relate to then electrons, because light allowed scientists to understand more about the electron, because we can't see electrons, but we can see light. And so we would just kind of play around with the models until it matched what we saw in terms of light being emitted from different elements and stuff. So yeah, so plants just do what we do in reverse, but they get their energy from sunlight, all right? So we will talk about light here in a few chapters. So first we'll talk about light, and then how light helped us learn more about atoms. Okay, so this chapter has a lot of concepts, and I feel like these concepts are the basis of a lot of comics and memes. Like, I'm a frequent lurker on the subreddit physics memes. They're very active. And so if you go on the physics memes subreddit, like half of them are about the double slit experiment, the electron wave duality of, or the particle wave duality of an electron. And so hopefully this chapter illuminates and helps you all understand the jokes, the inside jokes that come from like chemists and physicists when we're in a room laughing about a meme. Then you can feel included too, because you know about the wave particle duality of electrons, all right? Also, hopefully you can use these concepts that we learned about today. It's related to kind of everyday life, like the third phase of the Marvel Universe, like the whole premise, I'm not gonna ruin it for you, but the whole premise of like Endgame, all right? And Ant-Man and the Wasp, Quantum Mania, the whole idea of like time travel and like space-time bending stuff. If you watch them, who watched that movie, the Ant-Man thing? Maybe, okay, not a lot, weird, all right. Okay, the whole premise of that movie is that when you get small, like an ant, when you go into the quantum realm, stuff gets weird. That's like the whole premise of it, including time. And so that's what we're going to talk about in this chapter. Stuff gets weird when things are small, like in electrons. Okay, all right, so we got to talk about light. All right. Okay, so light in the most classical sense kind of comes from our physics definitions. If you take physics, I think 1251, that's E&M, electromagnetic radiation. That's when you learn about light and its wave properties. So we just need to get some definitions out of the way. So this is based upon our classical idea of light being this like infinite noodle wave traveling through space. So we can measure some stuff about that propagation of light traveling through space. We can talk about its wavelength, so measuring either two peaks or two troughs of that wave traveling through space. All right, so since it's a length, we can measure in meters, but more commonly, because light typically has small wavelengths, nanometers, which is times 10 to the negative 9. That's nanometer. I want this in a different color. And then oftentimes, because wavelengths is real small, angstrom is used too. So this is another common small unit. This is times 10 to the negative 10. All right, so that's wavelengths of our light. We can also talk about frequency, because light travels at the speed of light. Okay, we're not going crazy here, but light travels at the speed of light. And so if you think about those troughs traveling through space, if we kind of keep a stationary point and measure or count how many peaks pass a certain point per second, that's its frequency as that wave is traveling at the speed of light. So frequency, since it's a counting number per second, has the unit 1/seconds, but oftentimes is symbolized by a hertz. And so wavelength and frequency are related to one another by the speed of light. Light travels at the speed of light, so if we take its wavelength and its frequency, we get the speed of light out. So we see this inverse relationship. As wavelength gets shorter, we actually see frequency go up, because speed of light is a constant. And so just to check yourself the units here, speed of light is a velocity, so that's meters per second. Wavelength is like a meter, and then frequency is per second. So you see how those units work out. Meter times a hertz is a velocity. So that's how wavelength and frequency are related by the speed of light. Okay, so that's the wave nature of light. Okay, so we'll think about light in terms of, there's lots of different types of light we interact with on an everyday basis. Most light that we think about is visible light. All right, but you see visible light is just this tiny sliver of the entirety of the electromagnetic spectrum. We have high energy light, which includes like X-rays, gamma rays, and we have low energy light. And this is like infrared, radio waves, things like that. And so we can relate all of these things to one another: energy, frequency, and wavelength. So what we see here is that high energy light actually has a large frequency, or a large frequency, but a short wavelength. So those are the relationships you should get in your head. They're all related by equations, though I didn't bring up the energy one yet, but we do know frequency and wavelength are inversely proportional to one another. Short wavelengths are associated with high energy light, all right? So do know the general order of the energies of light. If you know the general order of energy, then you can, as long as you know the relationship between frequency and wavelength, you can make all of those relationships. So for example, if we look at visible light, we have like purple or violet over here, and then we have like red over here. So red light is low energy visible light, while violet is higher energy visible light. And we can see, scientists aren't very creative. If you look at the two different regions that flank visible light, next to red is infrared, right? We can't see infrared, but it is a type of light that's lower energy than visible. And on the other side of purple, our high energy light, is ultraviolet. So that's UV light, so what comes from the sun and gives us sunburn, right? So there's high energy light there. So do know the relative order of the energies. So since I know UV is higher energy than infrared, that means UV light, compare its wavelengths. UV light should have what kind of wavelength compared to infrared? Shorter, yes. So all of those trends should go together. So do know those. All right. Okay, so let's make sure we can math and do some calculations. So I already said that my favorite color is 490 nanometers. What is this frequency in hertz? So we're going to use our equation we just introduced. Speed of light is wavelength times frequency, and so these Greek symbols, wavelength is lambda, and frequency is nu. It's like a weird-looking V. It's a weird-looking V. Okay, and so the question gives us wavelength. So we are given wavelength. C is a constant, so we are solving for frequency. But do remember, speed of light is in the unit of meters per second. I'll rearrange this. So nu equals speed of light over wavelength. So speed of light is 3 times 10 to the 8 meters per second. So we need to make sure wavelength is in meters as well, because we can't just put whatever unit we want. But I give you this wavelength in nanometers. So let's remind ourselves, what does nano mean? Times 10 to the negative 9. So here's a trick. Since it says nanometer, I can just I can rewrite the number, but instead of writing nano, I just write times 10 to the negative 9 meters. And so if you put that into your calculator, you'll get something like 4.9 times 10 to the negative 7, but it means the same thing, right? Okay, so this is the number we want to put in our denominator. So 490 times 10 to the negative 9 meters. You can do the dimensional analysis too. Just trying to save you a step. And then we see meters cancels, and we're left with the unit of per second. And so that is a hertz. And so the answer down here is 6.1 times 10 to the 14 hertz. So that's a lot of troughs or peaks pass a point in space per second with this light. So 490, it's like between green and blue. All right, so that is wavelength to frequency. So let's do one more where we change frequency to wavelength. So it's the same equation. C equals wavelength nu, but this time we are solving for wavelength. And the only thing that kind of makes this question difficult is, again, units. Everything should be in meters, and then this question actually wants it in nanometers, because that's typical of visible light is usually depicted as nanometer light, a nanometer unit. So we'll just have to do that conversion afterwards. So speed of light is 3 times 10 to the 8 meters per second. Velocity is given 7.3 times 10 to the 14 hertz, but I'm going to write it as 1 over second, because then you can clearly see that the seconds cancel, and we are left with that meter unit. So the value of wavelength that's given here is, it's in the corner, is 4.1 times 10 to the negative 7 meters. That's what your calculator will say. But we want this in nanometers, so we go one step further. 1 meter is 1 times 10 to the 9 nanometers, and so we do get, in fact, a 410 nanometers out, right? So those are just some wavelength to frequency conversions, so definitely using those metric prefixes here is important. Okay, all right. And again, it's nicer to look at the number 410 nanometers. That's a nice number to look at versus 4.1 times 10 to the negative 7. That's not a nice number to look at. So this is why we typically report visible lights in terms of nanometers. Red light is like 600 to 800 nanometers. Purple light is about 400 nanometers. All right. Green light is like 615 nanometers. Okay. All right. So that is the wave nature of light, but that's not the only way we will talk about light in this class. So light is not just this like infinitely propagating noodle floating around at the speed of light. We had some new experiments come along to look at some other phenomena about light. So we talk about this wave-particle duality a lot. Light actually can both act like a wave and a particle. And so the one to really push this was Max Planck, where basically his entire scientific career, he would look at phenomena and try to write an equation to explain that phenomena. But he had a problem. So one of the phenomena that he tried to explain using constants and concepts was the idea of black body radiation. So you've actually experienced black body radiation. If you've ever used an electric stove, so in your head, turn on an electric stove, and what happens to the coils? They what? They turn red. They turn red, but specifically, they actually glow red. So go home and do this sometime. When you go home, turn on your electric stove, but turn off the lights. You will see it glow red. So that phenomenon, those coils are giving off red light, right? So what Max Planck did was try to, write an equation to describe that what's happening. And what he saw is that depending on the temperature of the object would change the color of the glow. So like blue stars are really hot, red stars are hot but not as hot. It's the same reason why your coils on your stove turn red hot. But the problem is when Max Planck tried to apply classical wave physics to answer the problem, he couldn't. It was impossible for him to answer the problem. So, or come up with an equation to describe the phenomena. So this is where he had to introduce the idea of a singular packet of energy that light can carry. So this has this kind of relates to the idea of like Millikan's oil drop experiment that said that, a single electron has this charge. We can say the same thing about light, that light of this wavelength can carry this minimum of energy. And so there's this kind of relationship there. And so Planck said that light is what we call quantized, that light can deliver this minimum amount of energy to an object that we can describe by this equation, all right, where the energy of a single photon, a single packet of light, is related to its wavelength, or so its frequency here. So the energy of a photon, meaning a single packet of light, is equal to Planck's constant times its frequency. But because we know that frequency and wavelength are related, we can also rewrite this in terms of wavelength, where the energy of a photon is equal to Planck's constant, speed of light, over wavelength. So it's here that you can see all of the different relationships between energy, wavelength, and frequency. As energy of your light goes up, if this number goes up, frequency has to go up. But if frequency goes up, wavelength actually has to go down to be consistent with an increase in energy. So wavelength gets shorter. So together, all these equations describe the different trends that we said. And it's all due to Max Planck that said we can't actually describe all the phenomena that we see using classical wave physics. We actually have to quantize light in order to do that. All right, so main idea in this slide is you can have a single packet of energy, a single packet of light that carries a specific amount of energy. So this energy that comes out is going to be really, really small, and that's the energy of one packet of light, just one. Okay, so let's talk about the experiment that really highlighted the particle nature of light, all right, and that is the photoelectric effect. And so this really made us truly believe that light is quantized. Light carries energy, and we can kind of treat light like a particle sometimes, like a photon. And so this work was done by Albert Einstein, and actually this is what gave him his Nobel Prize. All right, so it's weird. It's like you think of Einstein, and most people think of like his work in relativity and all that stuff, but his work in relativity was not recognized by the Nobel Prize community. It was actually his work in chemistry, and the photoelectric effect is what gave him his Nobel Prize. So small fact. So what is the photoelectric effect? So let me just set the scene. So Albert Einstein, he set up like a cathode and anode made of metal, and he would shine light on the metal surface. When the incoming light hitting the metal surface was high enough, electrons would get ejected from the metal surface, complete the circuit, he would measure a current. But electrons would only be ejected if the incoming light was a certain energy. He would keep increasing the energy of the light, and it would hit a certain point, and then electrons would start to be ejected. But anywhere before that, electrons would not be ejected. All right, and so there was this minimum energy required to eject electrons. We call that the work function of the specific metal, the minimum energy needed to do that. And so what he saw is that for every electron ejected, one photon of enough energy had to hit that surface. So one photon of enough energy would eject exactly one electron. And so this is what highlighted the particle nature of photons because of this conservation of energy. So let me show you a demo or like a simulation of what's going on. All right, so this is the experiment. I have a light here. I have a light. I can change the intensity of the light. Okay, so there are my photons. Okay, and then I can also change the energy of the light. I change the energy of the light by changing the wavelength. Does changing the intensity of the light change the energy of the light? No. All intensity does is change how many photons are hitting the surface. Okay, intensity is like amplitude kind of, but it doesn't change the energy. Okay, so let's see. I have the lamp on. Tell me, are any electrons being ejected from the surface? No. So what do I have to do to make electrons be ejected? I got to up what? I got to up the energy, but how? What do I need to change? The wavelength. I change the wavelength by doing what? Making it longer or shorter? Shorter. Okay, so I want to move, my bar to the left. All right, so at some point as I increase the energy by, there we go, by changing the wavelength to make it shorter. See, now you can see that electrons are being ejected, right? Okay, so electrons are being ejected right now. So we are above the light hitting the surface is above the work function of the metal. What happens when I change the intensity? So I'm making it smaller here. Come on. Are electrons still being ejected at this low intensity? Yes. But what about at this high intensity? What's the difference between those two things? Just more or less. So here you see intensity is just related to how many photons per second are hitting the surface of that metal. Because remember, only one photon can eject one electron, and that's it. So let's go back. Let me go to like medium intensity. So I'm going to go to a point where electrons are not ejected anymore. So let's go right here. Okay. Oh, nope. Go. Right there. Right there. Okay. So at this point, at this energy of light, are electrons being ejected anymore? No, they're not. So the only way, Einstein said, the only way to get electrons to be ejected is if the energy of the incoming light is high enough. So I'm too low right now, so I'm not going to get any electrons to be ejected. Even if I make the intensity crazy, crazy high. I can make the intensity really, really, really high, but remember, intensity does not change the energy of the photon. All it does is change how many photons are hitting it. So I just have all these low energy photons hitting the metal surface. They're not ejecting anything, no matter how intense I make the light. The only way to get electrons to be ejected is if I change the energy to be high. So let's look at this point where electrons are being ejected. What is the difference between, 500 nanometers and let's say 200 nanometers? The speed of what? The electrons. So you tell me, these electrons right here at 200 nanometers of incoming light, do they have high or low kinetic energy? High kinetic energy, okay? Then let's go back to these ones, these 500. Do these electrons have a kinetic energy? Yeah, they still have kinetic energy, they still have mass, they're still moving, but they just have less kinetic energy. So low kinetic energy of those electrons. When I up the energy, high kinetic energy. Okay, so let's go back to the slide and put it all together. Okay, so we already talked about this. So the energy of a single photon is related to its wavelength or frequency. So we already said h nu or hc over lambda. And so we already said if a lot of photons hit the metal surface, a lot of electrons are ejected, but only if we're above the work function. If we're below the work function, changing the intensity does nothing. Okay. And so we changed intensity, but we also changed energy. So we said if higher energy photons hit the metal surface, we saw electrons with really high kinetic energy get ejected. All right, and so this is due to the conservation of energy. So let's think about this. If the incoming electron, So let's pretend the work function of the metal was like 4 joules or something. And the incoming photon, I'm just making up numbers, had 5 joules of energy. What is if we have conservation of energy at play here, what's the kinetic energy of the incoming the ejected electron? 1 joule, yes. And could you, in theory, calculate the velocity of that electron if you set this equal to 1/2 mv squared? Could you calculate velocity? Yes, you could. All right. So that's at, above the work function. Let's pretend the incoming photon had, 8 joules of energy. So we see at 8 joules of energy, doesn't the ejected electron, have to have 4 joules of energy? So all that extra energy that you're bringing to the surface via the light is going towards the ejected electron. So any extra additional energy you supply it is going to make the electron move faster because of conservation of energy. So for funsies, let's pretend the incoming photon is under the work function of the metal. If we're under the energy required, will an electron be ejected? No, so let's check. So let's pretend that the photon that we're sending to the metal is 3 joules. The work function of the metal is 4 joules. What is the kinetic energy of the electron? -1, -1 joules. Okay, solve that. If the kinetic energy of the electron is -1 and you do 1/2 mv squared, what is velocity? It doesn't exist. It's an imaginary number. But what does our intuition tell? We learned that if we're under the work function, an electron is not ejected at all. It has no velocity because velocity here with a negative kinetic energy is an imaginary number. All right, so that's why under the work function, no electrons are ejected at all because there's no solution to this. All right, but if we're above it, then we do get a positive velocity that comes out. All right, so that's some just conservation of energy, and this experiment was very important in highlighting the photon nature of our electrons. It's not just waves anymore. It's not just wavelength and frequency. This energy component is super important and will come into play when we talk about our atom here too. Okay, so photons, they're particles, so you can count them like particles. So let's determine the energy of these photons. So I have 204 nanometer light. Let's calculate the energy of 1 photon. So that means we use Planck's equation here, where the energy of a photon is h nu, or if we're doing wavelength, it's hc over wavelength. So this is just plug and chug into this equation because we just want the energy of 1 photon. All right, so 204 nanometers is 204 times 10 to the -9 meters. I need that for this equation. So the energy of this photon is equal to Planck's constant, 6.626 times 10 to the -34 joule second times speed of light, so 3 times 10 to the 8 meters per second, over wavelength that's given, so 204 times 10 to the -9 meters. And just to show you that the units all work out, meters cancel, and then seconds cancel. So we see that the unit we're left over is joule. And so plug this into your calculator, you get that the energy of 1 photon is 9.74 times 10 to the -19 joules. Is that a lot of energy? No, that is not a lot of energy. So if we think about like how much energy it takes to heat up water, right? The specific heat of water is like 4.18 joules is required to heat up 1 gram of water, 1 degree Celsius. So this 1 UV photon isn't going to do anything to that of water, right? But the thing is, just like atoms, we never work with 1 of anything. We work with moles worth of stuff. So if we can count 1 photon, we can count a mole's worth of photons. So a number that's actually more useful to us is to report the energy of this light in a per mole basis, because that's what we're going to be working with. We're never just going to work with 1 photon, one packet of light. We're working with a ton of them. So what we want to do is actually just scale this value up, because this is the energy of 1 photon. So there's hopefully in your mind you think, oh, I just need to multiply by Avogadro's number. So I'll just do the dimensional analysis here. So I'm going to rewrite this number. So this is how much energy is in one photon. So I want to get this into a mole's worth of photons. So I'm going to put Avogadro's number here up top. So I'm basically multiplying by Avogadro's number. All right. But right now, if I look at the units, this is joules per mole. It's best to put this in kilojoules, and you'll see why. So let's convert this joule amount to kilojoules. So 1 kilojoule is 1,000 joules. And so you see that the answer here is 587 kilojoules per mole. That's a nice number to look at. 500 kilojoules per mole versus like a joule value would be like in the tens of thousands, right? So reporting these energies in terms of kilojoules per mole are very useful if we're thinking about like energy density of like lasers or light sources. Kilojoule per mole is nice to use. We just have to remember that photons, when we use Planck's equation, E equals h nu, that's the energy of one photon. But if we want a mole's worth of photons, we got to scale it up and basically multiply by Avogadro's number. We can count them, like we can count atoms, right? Okay. All right. So now let's talk about why light is important. Because the thing is, we can't, and I mentioned this before in chapter 2. The scientists, when we talked about the inner workings of our atom, our different models of our atom, the model changed when new information was observed. All right? Because the thing is, we can't see atoms, we can't see electrons, but we can see other stuff. And so the other stuff that we observed in this second phase of changing of our atomic structure diagram is light. Light is crucial in us understanding electrons in our atomic model. Because if we look back in chapter 2, we went from Dalton's model, no electrons, plum pudding, then Rutherford's model that said there's this electron cloud, but there was no details. It just said, oh, electrons are on the outside, but no other details other than that. So in this part of the chapter, we will look at more way into detail of, okay, yes, electrons are on the outside of the nucleus, but there's actually a lot more structure there than just, oh, they're on the outside. There's a lot of details here. So we are here. We're going to talk about the Bohr model and his different postulates to come up with the atomic model. But his model isn't 100% correct. It's actually, the Schrodinger equation is 100% correct, but the Bohr model gets us there like 95% of the way, right? So the Schrodinger equation, you actually have to solve it using quantum mechanics, but we're not going to do that. But that's how we get our quantum numbers. So we'll still talk about it. Okay. Okay, so light, again, is important. Light has energy, and this is what scientists use to deduce the electronic structure or the atomic structure of our atoms. And so what they saw is, depending on what kind of sample they were working with, if they would excite a sample, they actually saw different samples emitted different colors. All right, and what do I mean by excite? They would just fill up a tube of hydrogen gas and they would plug it into a wall socket. They would fill up a tube with neon gas and they would plug it into a wall socket and it would glow. That sounds a lot like a neon sign, right? Because it is a neon sign. So a neon sign, you're actually looking at the line structure, the line spectrum of neon. So the neat thing here is that all elements emit different lines, and that's what's here. We see different lines for different elements. So hydrogen can be separated or distinguished between neon. And so these differences in lines give us insight into what's going on with the electrons inside the structure, all right? And so the problem is with the Rutherford model, okay? The Rutherford model could not properly explain these lines that they were seeing, so that means, hey, we need a new model, right? And that's where the Bohr model comes into play. And so these lines that we see, they do come from the colors of the rainbow, but it's not continuous light. Like white light contains all the like red, orange, yellow, blues, whatever in the rainbow, but these line spectrums are only very distinct wavelengths, like only 486 nanometers. It's just one line. So it differs from that of a continuous spectrum. All right, so we're going to take these lines and figure out what they mean. So basically, those lines come from electrons. Electrons moving up and down in an energy level diagram on our atom. When electrons relax back down to the ground state, they emit light. All right, and so what Bohr said is the only way we can describe these light patterns is by giving electrons certain energy levels that they're allowed to be in. All right, so these energy levels you can think of like as rungs on a ladder. I can have an electron here, or here, or here, but if I put an electron up here, is that electron stable up there? Is it going to stay there? No, it's going to fall back down until it gets to an energy level. So our electrons can only live in certain energy levels, all right, for that atom to be stable. And so we number these energy levels, n, 1, 2, 3, 4, so we just use integer values, where n equals 1 is the lowest ground state energy, and this is the state that's closest to the nucleus. So you can see like these little concentric rings, n equals 1 is closest to the nucleus, while n equals 6 is furthest from the nucleus. All right, and so you can, again, think of these as rungs on a ladder, that an electron cannot exist between the levels. They have to be in n equals 1, 2, 3, or 4. But most of the time, the electron is going to be in the lowest allowed energy level, n equals 1. Because if you think about it, like if you have an electron, or if you are an electron, are you going to feel the safest when you're on the top rung or on the bottom rung? Where are you going to feel safest? On the bottom, yeah. So you're going to spend most of your time in n equals 1 if you can help it. All right. So we call that the ground state, while we call the electron being in any other above state the excited state. So electrons aren't going to stay in the excited state long. They're going to always fall back down to their lowest level ground state if possible, and usually emit light in the process. So this is the first part of Bohr's model. We've set up the rungs on our ladder. And so another chemist came about and calculated the actual energies of each of these levels, right? So they saw that the energy, so see how so this is like the ladder. This is the ladder, but the first rung is here, the second rung's here, the third one's there, and then they start getting closer together. So on an actual atom, the ladder, the rungs are weirdly spaced, not like on our nice equal ladder up here. And so we had Rydberg was another chemist who actually predicted the energies of each of these levels using this equation, where the thing to note is n, that energy level value, is embedded into the equation. So based upon whatever energy level that electron is in, will dictate what energy it is on this energy level diagram. All right. Okay, so those are the rungs on the ladder. Okay, so let's look at some other details. So here's again another energy level diagram where we have n equals 1, 2, etc. And on my y-axis, this is energy of those electrons. So I could have an electron here, and n equals 1, n equals 2, etc. All right, so if you look at these energy values that are predicted from the Rydberg equation, they're all negative values. And remember, in chemistry with potential energy, that's okay. Negative potential energies are okay because negative potential energies are related to attractions. All right, so that electron is attracted to the positively charged nucleus, and that is why energies are negative. Energies are stable. Remember in chapter 5, we talked about potential energy is lowest, most negative when things are close together and attracted. So that's why we see negative potential energies here, right? So these are all negative values, and that's good. So then we also see why do each of the energy levels, why does energy increase as n increases? So let's just take it back to chapter 5. We said Potential energy is lowest, most negative when things are attracted and close together. So as n increases, I actually increase the distance between my electron and my proton. So we should see potential energy go up. And that's what we see here. If we remember back from chapter 1, the potential energy diagram, as D increases, as we move along left to right on this graph, as D increases, that's because N increases. And we do see potential energy increases when we do that. It gets closer to 0, right? So again, it all falls back on, in chemistry, potential energy is lowest, most negative when things are attracted and close together. But as we increase N, distance increases, so our potential energy increases. Actually, I just thought of this. Think about our ladder analogy again. Think about in physics. How do I change my potential energy? On a ladder, I climb up it. And if I climb up the ladder, how am I changing my N? Increasing it, yeah, because I'm going up the rungs, yeah. So the same idea. That's why my potential energy is increasing, right? Okay, all right. Also, something to note. See how in the actual energy diagram, the energy levels converge. They start to get closer and closer together. So we have like n equals 1 to 2 is the biggest jump. Then they start getting closer and closer. That's a very important point that we'll talk about in a little bit. We don't see equally spaced rungs. They get converged. And it has to do with the Rydberg equation that n value is in the denominator. That's why, right? But do keep that detail in mind. Okay, so, all right, postulate 2. Okay, postulate 2 just says why we need energy levels. And so postulate 2, so if you think about it, an electron and a proton, they're attracted towards one another, right? So if you just let an electron and a proton hang out, won't they just like come crashing into one another? Wouldn't you think that that's what would happen? If you had like a positive and a negative magnet, they're just going to come crashing into one another. Unless you put something there to stop it, like an energy level. And so that's the big idea here. And you'll talk about this in your lab EMS. I think you do it after fall break. I hope so. But with Rutherford's model, there is no energy levels. So if we modeled Rutherford's electron and proton, we would actually see the electron just come spiraling in to the proton. They would crash into each other and produce a nuclear explosion. We know that doesn't happen in real life. So that's why we know Rutherford's model doesn't exist. So this phenomena, a not stable atom, a huge explosion, will happen if we don't have energy levels. So now let's put the ladder there. Let's put the energy levels there. Now the electron has a nice stable place for it to stay, so it does not go crashing into the nucleus. And so the analogy I like to use is, okay, if there is not a ladder and you would pick me up off the ground and drop me, and then everyone laughs, yes, I would go splat, right? I would not be very stable. Versus if you picked me up and there was a ladder present and you dropped me, I would land on the ladder and I'd be nice and stable and I wouldn't go splat. And so the idea here is we need those energy levels for the atom to stay stable. If not, then we're just going to go crashing down and then not be stable. Okay, so second postulate just says why we need those energy levels. Okay, so let's talk about the third postulate, and this is where light is finally involved. Okay. So let's think about the rungs on a ladder again. Okay, if I wanted to go up the ladder, do I need to put energy into the system or does energy leave the system? Into, yeah, so delta E would be positive if I want to go up the ladder. Okay, and so the big idea is for every step that I take, right, every step that I take, the energy between these two states is always, there's always some type of photon related to that for each energy difference of states, right? I can only move between like levels 1 and 2 or 1 and 3. So these energy differences always have a resulting photon related to it because photons can be related to energy, right? Energy of a photon is equal to hc over lambda. And that's where light comes into play. The energy differences of these rungs is equal to that of the energy of a photon. All right, and so that's what this slide says. Okay, so energy differences here, okay, of our atom. There's always some type of photon related to it. Okay, but it's up to us to understand, is a photon emitted or absorbed? So just like in chapter 5, where we talked about exo versus endothermic, but we talked about energy in terms of heat. Just replace the word heat with photon. Photon is pure energy. It's light energy. So in an exothermic combustion reaction, heat is released. But in an exothermic reaction involving light is released instead of heat. All right, and so that's the big difference. And so what we see here, the third postulate, it says that light is only involved when an electron is either going up, moving between energy levels. That's the only time light is involved. When an electron goes up the ladder, light is absorbed. When the electron comes falling back down off the ladder, light is emitted. But if you just have an electron sitting there on the ladder, it's not doing anything with light until it starts moving around. All right, so let's think about if the electron goes up. If an electron goes up to a higher energy level, is energy emitted or absorbed during that process? Absorbed, so that means light is absorbed, okay. If the electron comes falling back down, energy should be released, so that means light is released or emitted. And so that's the big idea. And so we see here the energy difference. So, okay, pen. All right, so if we looked at these two energy levels, so like going from 1 to 2 and 2 to 1, we can calculate the wavelength to go from 1 to 2. Right, it's like, so, I don't know, I'm going to just make up a number. I'm going to say like 250 nanometers to go from N1 to 2. But 250 nanometers of light is absorbed. But if we want to go back down from 2 to 1, 250 is still involved, but that light is actually emitted now because it's all related to the energy difference of those two levels. Okay, so, so just like in thermo, we need to think about, you know, is my atom gaining or losing energy? So if your hydrogen atom absorbs a photon, absorbs energy, that means your electron's jumping up to a higher level, N increases. Because your atom increases energy, this is an endothermic process. Your atom is gaining energy. Versus if your hydrogen atom emits a photon, energy is being released. That's an exothermic process. So typically we'll see N decrease or the electron fall. And so it's all about signs again, right? Signs always mess us up, but that sign is just telling us, is energy being released or absorbed by the system, right? And then the wavelength calculation, we can take the Rydberg equation, the final and initial energy levels that we start with and end at, and that energy difference is related to the photon that's either emitted or absorbed, and then we can go ahead and use our Planck equations to calculate the wavelength of that photon that is involved. But it's up to us to understand positive or negative here. Okay, so let's do, are we going to do an equation? No, not yet. So let's do a conceptual question with this idea of electrons transitioning. That's the only time light is involved. So here I have 3 different transitions, A, B, and C, and then I have 3 different lights, 1, 2, and 3. Tell me which transition is with which light. So to guide you, ask ourselves, what is the difference between lights 1, 2, and 3? Let's compare their wavelengths. Which one has the shortest wavelength? 3? 1. Yeah, so we're measuring distance between troughs. So this is the wavelength. So this one has the shortest wavelength. So that means 3 actually has the longest wavelength. So the distance between peaks, longest wavelength. Okay. Okay. But the problem is, does this diagram, is this wavelength? No, this is in the unit of energy. So use the relationship. How is wavelength and energy related? Short wavelengths have Big energies. So the long wavelength is going to have a small energy. Okay, now can you answer the question? Which transition involves light source 1? A, B, or C? A, because A has the largest energy gap, right? The energy of the atom, the changing of the atom, is equal to that of the photon that is produced. So big energy change in the atom, big energy of the photon that's emitted. Okay, and so what transition is 3? C, yep, because small energy, small little energy gap. Small energy, so long wavelength, and then 2 is B, so ABC. Cool. All right, let's take it a little bit further. So I just said these are the wavelengths involved, but based upon the diagram given, are these is this light being absorbed or emitted on this atom? Emitted, how do we know? Yeah, the electrons are falling. Yeah, so that electron is going from a high energy to a low energy, so all that lost energy is going to emitting this light. So this is emitted. Okay, all right. This is a common conceptual question on exams, but there's a very specific strategy we take. Okay, so which of these transitions for a hydrogen atom corresponds to the emission of a photon with the shortest wavelength? So this is like reading comprehension. Just take it one step at a time so we know what we're looking for. So the first word, emission of a photon. What kind of transition are we looking for? Yeah, down, which means we are looking for the n value falling. Yes, falling. So hopefully that eliminates half of them. Does that eliminate half of them? Yes, it eliminates the first two, because in those ones, the electron's jumping, right? And so that would be absorbing a photon. So we don't actually want those ones. Okay, so that's the first term. The second one is shortest wavelength. But those energy diagrams, it's not in wavelength, they're in energy. So I like to relate everything in terms of energy. So short wavelength means what in terms of energy? Big, or yeah, big, whatever, large. So what we are looking for is a large drop. All right, so then the next part might be kind of the hardest part, is draw an appropriately spaced diagram and look for the largest drop. So there's 4 levels, so I'm going to draw 2 different diagrams. 1, 2, 3, 4. Okay. Okay, so this is n equals 1, 2, 3, 4, or is the diagram 1, 2, 3, 4? The first one or the second one? The second one, yeah, so it is not the first one. I'll show you why if you draw the first one, you will get in trouble. Okay, so let's use the second diagram here, the correct one, to figure out which one is the largest drop. So we're going from 4 to 2, and then we're going from 3 to 1. So what is our answer? D, yes, D results in the emission of the photon with the shortest wavelength. It has the largest energy. So that photon from 3 to 1 has the largest energy. Okay, let's pretend you drew the diagram wrong, and let's use diagram 1 and see if we can't answer the question. So 4 to 2 and 3 to 1. Could you answer that? No, if you equally space them, they look like the same energy difference, right? But they're not equally spaced, that's the thing, okay? So if you draw it wrong, you will get this wrong. Or I guess then you would not know how to answer it. So yeah, you can't draw the diagram this way. And so the reason I love questions like this is it's so easy to change this question. I could change it to, instead of emitted, I could say absorbed, and the answer changes, right? Or I could change shortest wavelength to longest wavelength. Or I could just not say wavelength. I could say which one has the largest frequency. Or I could say the smallest energy. And so there's so many combinations of ways I can ask this question. We like questions like this. They're conceptual. You still have to know all the basics of the Bohr model and how energy is related when photons are involved. So yeah, and there's many, many ways we can ask it. all right? But it's still the same strategy, that's the thing. Always relate it back to energy. Think, am I looking for a jump or am I looking for a fall? Or a jump or a drop. Okay, so let's do the calculation-based one, all right? So in all the other ones, they were just conceptual, right? Like we were just saying like high, low energy, short, long wavelength. So let's actually calculate the wavelength of a photon that is emitted when it undergoes this transition, 4 to 2. Okay, so we could draw it. We should be able to tell that this is emission because we're going from 4 to 2. A photon should be emitted here because we're falling. All right. So the idea here is that the atom undergoes a transition, and the absolute value of that energy change is related to the photon that's emitted. The sign of delta E atom just tells us the direction energy is going. I don't want you to get confused when you get a negative wavelength. That negative sign just tells you energy is being released, so that photon's being emitted. So that's why I have this equation over here, all right? We just want to take the absolute value of that energy change, and that's related to the photon that's involved, but it's up to us to recognize, is it absorbing light or is it emitting light? Okay, so I think it's just plug and chug. So it's final minus initial, they're in the denominator and they're squared. So in this fraction, it's 1 over final. So 2 squared minus 1 over 4 squared. So this is 1 over 4 minus 1 over 16, I think. I think I did that right. And so when you do that math, that parentheses terms ends up being 0.1875 positive. And then we multiply that by this constant that's out front. So negative 2.18 times 10 to the negative 18 joules. So we see that the atom actually loses energy. So negative, it loses negative 4.087 times 10 to the negative 19 joules. The atom loses that energy. Is that consistent with what was told? The electrons going from 4 to 2. So yes, the atom is losing energy. So that means a photon is emitted. So we're going to take the absolute value of this answer and then relate it to the energy of the photon. Okay, we just want the absolute value. The sign just tells us which way light's going. In this case, it's being emitted. So that means the energy of my photon, 4.087 times 10 to the negative 19 joules, is hc over wavelength. That's what I'm solving for. hc is their constants, so 6.626 times 10 to the negative 34. Joule second, speed of light, 3 times 10 to the 8 meters per second. We're solving for wavelength here. That's what we're solving for. So looking at the units, joules cancels, seconds cancels. So you see the unit that's left is meters. So when you solve for wavelength, you get a meter amount, so 4.86 times 10 to the negative 7 meters. But we want this in nanometers because this is like really nicely in the visible region. Okay, no one likes scientific notation, so for every 1 meter, 1 times 10 to the negative 19 nanometers, so that is 486 nanometers. So very, very close to my favorite color. So it's like right between blue, green. All right, so I was just solving for wavelength. So what I did is I moved this over there and that over there. Okay, to get that. All right. All right, so that's the numerical one. Which ones do we like more, numerical or the conceptual question? Conceptual, yeah. Okay, so that is the line. So let me just point this out. So 486, that's like green light. And this is of our hydrogen atom. So let's just quickly look at the line spectrum of hydrogen. So which line is it? The first, second, third, or fourth line? The third one. Yeah, you can barely see the purple one, so I'll mark them. So we have this line, this line, this line, and that line. So what line we just calculated was this one right there, but right between blue and green. All right. All right, so that's the significance there. All right, so we have 15 minutes left. Wow, great. So let me do a demo. Okay, demo. So we talked about light and how light is important for us to understand the electronic structure of our atoms. So I mentioned before that all elements have different unique line structures. And so I just showed you the line spectrum of hydrogen, and it had those 4 lines. So let me show you the line spectrum of some other elements. And we'll see that they're all unique and they're all cool. Okay. Okay, this is a little dangerous. Okay, so all elements have different line spectra. And so what we'll basically see, we're just going to see the brightest line. We're not going to see all the lines at the same time. We're just going to see the brightest line. So let's do calcium 2+ first. All right, so this one's like not super fun. It's just like orange, right? So what we're seeing is just the orange lines off of the line spectrum. Because the idea here, actually I forgot to preface this. So we see light is emitted when electrons fall. Okay, so the point of the flame is I'm putting calcium atoms through this. I'm exciting all of those electrons all high up, and then they're going to come crashing back down, releasing photons at the same time. So that's what the point of the fire is. I'm just exciting everything at the same time. All right, so that's calcium. Let's look at, where's lithium? Lithium. Yeah. Yes, this one is evilly looking. Yes. So lithium, obviously different than calcium. Yeah? Okay, all right. Okay, that's lithium. What do we want to do next? Strontium says deep red. Oh, geez. Yes. I don't know. Lithium was better, I think. Okay. What do we want to do next? Let's do potassium. Potassium. Ooh, what color is that? Lavender. Yeah, it's like pink, or it's like a purpley. Yep. Okay. All right, we'll do nickel 2+. Okay, this one says peach, but I don't know about that. I think this one's broken. Okay, and then the last one is the best one, is copper 2+. Anyone make a bonfire and they put like copper pipes in the bonfire? Yeah, this is good. Yes, yeah, so always save your, if you're doing some plumbing work, just save those copper pipes in your garage so when you do a bonfire you can throw them in. And then it turns green because what you're seeing is the line spectrum of the copper atom. Okay, all right, there we go. So those are the line spectrums. That's why light is important. We can see light, but can we see electrons? No, the light gives us insight into the energies, the energy changes that electrons are undergoing in their energy level diagrams. Light just gives us insight into that. Okay, there we go. All right, we got like what, 10 minutes? Yes, so let's talk about other stuff. So we talked about light. Light is a wave, but then we shortly introduced that light can be considered a particle, a photon. So a wave can be a particle. So is it that much of a jump to say particles can be waves? Yeah, right? If a wave can be a particle, maybe a particle can be a wave. And that's what Louis de Broglie said. Right? He actually said this in his PhD thesis. So he wasn't even like he was just a grad student at the time. And he proposed the idea, hey, if light, a wave can be a particle, maybe a particle could be a wave, and he ended up being right. And so this was an example where like someone just like guessed something, and it was later that experiments came about and like proved that they were right. Right? So it was pretty impressive of him. So the big idea here is that, okay, yeah, light is a wave and it can be a particle. So let's apply the same concept to an electron. An electron is a particle, but hey, maybe sometimes it can be a wave. And so that's what de Broglie said, that an electron is a wave, and when an electron is in an energy level, it's actually a standing wave around that atom. Okay, so this is aiding to the wave characteristics of an electron. And so I said that this is an example where de Broglie came up with this hypothesis, this theory, but had no data to back it up. And it wasn't until later that folks actually did measure wave properties of electrons, right? So an example of a wave property is diffraction. Diffraction is when we either have constructive or deconstructive interference of waves, how they propagate, like how they line up. So X-rays, or even like diffraction off of like the back of a CD or something, light can either constructively or deconstructively interfere with one another. You get these weird patterns. That's X-rays, like that's light. But later, we learned that electrons can actually do the same thing. They can diffract too, but electrons are particles. But in this experiment where we're using electron diffraction, we're actually utilizing the wave properties of electrons, which was crazy because, you know, de Broglie came up with it first, but then the evidence came later, all right? And so the whole idea, de Broglie says that all matter, as long as it's moving through space, has a wavelength. Right? So wavelength, de Broglie wavelength for a particle moving through space is related to Planck's constant, its mass, and its velocity. Do not get this confused with our other wavelength equation that said energy of a photon is equal to like hc over lambda. So here's an example where lambda is used in two different equations, but these are completely different. This equation is talking about the energy of a photon. A photon does not have mass. This equation is talking about the wavelength of an object, okay, which, again, it was crazy for de Broglie to even say, but he ended up being right. Everything has a wavelength, but it's in an electron where it's super important, because let's think about it. Electrons are really small, right? They're really small. So if we have a really small number in the denominator, what is the magnitude of wavelength? If we have a small number in the denominator, wavelength is big. Big enough that you can actually measure it, right? And so that's what it is, that an electron is super, super small, so they actually have fairly large wavelengths that we can measure, all right? So let's calculate it. This is just plug and chug. Let's calculate the de Broglie wavelength. And so again, remember, there's two ways we can calculate wavelength. So when you're doing homework, look for, is a mass given? If a mass is given, it wants the de Broglie wavelength. But if I'm just talking about like light, a photon, then you use the other equation, right? But here, the de Broglie wavelength relates mass and a velocity to a wavelength. So it's just plug and chug. There is the electron. There's its speed. So we just plug stuff in. So wavelength equals Planck's constant, 6.626, times 10 to the negative 19 joule second. Joule second. There we go. Over mass, so 9.11 times 10 to the negative 31 kilojoules. So do recall, joule, the unit of a joule is a kilogram meter squared over second squared. So we want mass to be in kilograms. All right, so if you're given in grams, do make sure you make that conversion to kilograms so it's consistent with a joule. And then velocity is given 5.97 times 10 to the 6th meters per second. All right, and so we can see, so I was just looking to see how the units cancel. So kilograms cancels, one of the seconds cancels, the other seconds cancels, and then one of the meters cancels, so we see that we're left with just a meter. So just making sure that all of this is, all the units work out. So you put that in your calculator, you get something like the wavelength of this electron traveling at this velocity is 1.22 times 10 to the negative 10 meters. So yes, that's fairly small, okay, times 10 to the negative 10 meters, but this is on the scale of an atom. An atom is in the angstrom realm, so we could rewrite this as 1.22 angstrom, All right, so like an angstrom, that's how big an atom is. All right, so the wavelength of an electron is on the scale of a single atom. All right, so what do wavelengths, why are these important to us? Okay, the idea that, electrons can be particles or waves, this whole idea of wave mechanics gives us this new type of math. So classical mechanics utilizes, conservation of energy, what we call deterministic theory, where if I kicked a football across this room, I could measure its position, velocity, acceleration, anything about that football at any point in time. That is classical physics. That's what you learn in physics class, right? You throw a ball, it's like angular moment, like everything about it, right? But when things get really small, stuff gets weird, and that includes electrons, right? So that's where this new type of math comes into play, where instead of talking about certainties, we talk about uncertainties. And that's where Heisenberg comes up with his theory that says you have to have some minimum amount of uncertainty. And then this principle becomes really, really important when stuff is really small. When stuff's really small. So here's the analogy I like to use. Let's go to a NASCAR track, right? And the cars are going like real fast, right? You can imagine that? Okay, they're going real fast. What would happen? So actually, let me describe what the Heisenberg's uncertainty principle says. It says that the uncertainty, the uncertainty in a particle's position times the uncertainty in its momentum or its velocity has to be above some minimum. So basically, we can't know position and velocity 100% all the time. That's the big idea. So let's go back to the NASCAR track. They're moving around in a circle. What happens when I take a picture of one of those cars? If I take the picture of a car going around the track, do I know a lot about its position or its velocity? Position. I know for certain its position, but do I know anything about its velocity in that picture? No. So at that moment, I know for certain its position, but I lose everything about its velocity at that moment. So that's how we don't violate the uncertainty principle, because we don't know one of the things, so we stay above that minimum. Versus, let's say we're still at the NASCAR track and we use a radar gun and we get, the car's going, 100 miles per hour or something like that. So at that moment, when I clock the speed, I know a lot about its velocity, but do I know anything about its position? No. So that's why we still maintain Heisenberg's uncertainty principle, because we still have large uncertainty about one thing, even though we have certainty on another thing. And that's the big idea with electron orbitals. So these shapes, all right, is the reason. S, P, D, all of these shapes, these are probability maps of finding electrons, because we aren't allowed to know their position very accurately. I can't know the exact position. So I'm going to say, I'm like 95% confident that the electron is in this space. And that's how we get around not violating Heisenberg's uncertainty principle. And so the last part here, we got 3 minutes, we can calculate and use Heisenberg's uncertainty principle given some information. So we're just saying delta x is uncertainty in position. Delta mv, this is uncertainty in momentum, and it has to be above some minimum. And this is all a constant. But if mass stays constant, I can actually take mass out. So this is position times the mass of the object, because the mass of the object's not changing, times its uncertainty in velocity. All right? And then at this point, it's just math, but we need to make sure that the values here are good. So given this question, I tell you we have an electron and its velocity is 5.997 plus or minus 0.05 times 10 to the 6 meters per second. So how this is given is in terms of velocity plus or minus its uncertainty. So we actually just care about this value. We don't really care about velocity because that's not given in the uncertainty equation. So I'm going to just rewrite this so you can clearly see what's what. The velocity of this electron is 5.97 times 10 to the 6 meters per second. But its uncertainty is 0.05 times 10 to the 6 meters per second. This is the value we're going to plug into that equation. Okay, we're actually not going to use the 5.97. We don't need it. Do we know the mass of this electron? Yes. We know the uncertainty and velocity. All of these are constants, so we are just going to solve for uncertainty and position. So the equation here is delta x, that's what I'm solving for, is the mass, so 9.11 times 10 to the negative 31 kilograms, equals uncertainty and velocity, so I'm going to use the 0.05 times 10 to the 6 meters per second, greater than or equal to Planck's constant, so 6.626 times 10 to the negative 34 over 4 divided by pi. Yes, this is the same pi, so 3.14. All right, and so you just solve for delta x, and that is the minimum amount of uncertainty you have in your electron, given that uncertainty and velocity. All right, so we're about halfway done with chapter 6. Hopefully we'll finish chapter 6 next Tuesday, but chapter 5 homework is due on Monday.